Hey, just wanted to give a quick demo of Squiggle. That's a little language or DSL that I've been making. So Squiggle is basically kind of like Guesstimate, the programming language. There's a lot of exploration to be done. It's still very early. Still like messing around with the basic concepts. But I think so far it does show some promise. So I wanted to give you a quick demo. So the first thing is that with Guesstimate, everything was done via sampling. So in order to generate a distribution, we'd use samples. That doesn't work well with long tails. In long tails, you'd prefer to use like analytical methods. So for a lot of distributions, 5.2, you could see that over here, it's more of the numerical method of figuring out what the PDF is at every point in time. And then here underneath is a CDF to that PDF. This just has some functionality to allow you to mess with it, to change between CDF and PDF, and to view it in linear log space, depending on what you're interested in. So that's like a simple normal distribution. There are cases where if you want to do multiplication on two different distributions, or if you want to do a lot of mathematical operations, it does become nice to use sampling. So in those cases, if you do normal 5.3, then you'll see it automatically does sampling. Right now, you could just change the number of samples and the specific way that it does the kernel density estimation to smoothen it is that output XY points, which is something that you may want to configure in the future. Hopefully we'll have better, more sensible defaults. That's all like kind of here. One thing that's common is for people to use multimodal distributions, or that basically is a mixing of different distributions. So if I could do multimodal, normal 1, 2, and then I'll have 5 to 10. Oh, interesting. Say like normal 10, 1. Okay, yeah, I think I'm not using, it's still new. So basically, if I use the letters MM right now, that means multimodal. So as you could see here, this is like 50% of the mass is on this normal distribution, 50% is on this one. I could also use like log normal distributions or whatnot. It doesn't matter too much. This is like an extreme log normal. For intense log normals, it's nice to be able to look at them in log space, right? And one nice thing is that if I multiply this by a constant, then it's just going to use numeric methods to figure out like what the solution is. If I multiply it by a distribution, then it's going to use points, or it's going to use simulations. If I only do that to one of the subdistributions, it'll figure out things accordingly. So in that case, it's a bit complicated, so I'll just do 30 to 35. Great. So you can see that this distribution on the right is smooth, and this one on the left is what the sampling was done to. So the sampling was basically done at this step, and then we use numerical methods for the rest of it. So a lot of the challenge is to get that to work decently. There's also a little bit in terms of discrete combinations. So you could say maybe some of the probability mass is in the points 2 and 4. So over here you have a mixed distribution where some of it is discrete and some of it is continuous. I could add a array on the end to basically say what probability mass is for each one of these 4 sub-items. So maybe that's 0.2, 0.4, 0.5, and 0.3, 0.4, or whatever. And you can see as I toggle this number, so if I remove this guy, then that'll make that one very uninfluential, or if I make it bigger, that'll make that one bigger. So, and one nice thing is that, of course, like as I type, it's pretty fast, so it's able to do things kind of quickly. That's also a nice benefit they get from not needing to sample all the time, because sampling definitely takes time, but when you don't need to sample, then you could save that. So I'm going to go back now to not sampling. So one great thing about it being a little bit of a language is that you could write functions, which just have a lot of nice properties. So let's just say I'm going to have a function of t, where foo t is equal to normal. I'm just going to pass in that t. And then I want to write foo down here. What this does is it basically, so it'll make sense in a second. So if I take foo of 1, foo of 2, foo of 3, so you can see that like as foo increases, this middle distribution here keeps on shifting to the right, right? So foo 100, foo 1000, so that's basically what happens. So if I'm looking at the function of foo from 0 to 10, or I could change that, maybe I'm interested in it from 0 to 100. Basically, this is a graph of the percentiles. This is a bit confusing right now, so I'm going to remove some of that complexity and it just broke. It's still, like I said, in beta. Foo t is equal to normal t. Sure, foo. Yeah. So basically, the different lines represent the different percentiles, and then it goes to the extremes on the ends. So at t equals 0, the mean is going to be at 0, and it's going to be evenly distributed. And then when t is 10, the mean is going to be 10, as you could see. In this case, the mean is at the point of the median, so it's simple enough. And if I want to change the diagram to focus on different lengths, I could do that, right? So the goal of this is to allow people to intuitively put together distributions while being able to edit them kind of quickly. So maybe in some cases, maybe t would be a bit of an exponential, and then maybe the uncertainty would increase as well. And maybe that would increase at a faster rate than the mean would increase. So it should be pretty easy to just like mess with this and see what it's like at different points. And then of course, like at any point, I could figure out what the value would be. So that's all well and good. Obviously right now we could only visualize 2 dimensions. In the future, it'd be great to be able to have 3-dimensional plots or more. But that's all like a lot of stuff that would come out and that we still need to do. So some areas where this is kind of fun. So I'm going to take this distribution. Here we go. So scale exponent. So what that does is basically every x point of the PDF is going to take the exponent of the x point, and then it's going to rescale the whole distribution to normalize it, so it has a full probability mass of 1. So if I, for instance, if the scale exponential is like very low, then that's basically going to make the distribution less certain, essentially. And if it's very high, then it's going to basically highlight the main, the most high probability parts of that. And this is a pretty nice way if you basically think that someone is too confident and want to automatically adjust, or if you think that they may be too unconfident and you want to basically rebalance that. So it's like a pretty convenient probability function for those scenarios. With scale exponent, like one kind of fun thing, although we don't use it too much, is you could do similar operations for addition and multiplication. So let's just take, this is one distribution, and just say I'm going to, in here it's, I think, dot times a uniform from 10 to 20, right? So what this is doing is it's basically multiplying them on the y-axis, and a uniform will just be flat, so it'll just be taking, basically filtering out everything between 10 and 20. I could change that, so if, I could lower it or increase it to give a better idea of what's going on. Or if I do dot plus, then that's basically going to take a uniform distribution and add it to everything in that space. It takes a bit of time to get used to that, and I don't know how common it would be, but it is kind of fun. Dot times is also, of course, like a naive Bayesian update, assuming that these 2 different distributions are totally independent from each other. So yeah, that's all pretty simple. Or that's all hopefully kind of straightforward. This is like one fun example of, we have the US economy, and it has some kind of growth rate per year. So if I want to plot the US economy, I could do that here. So I'm just going to say that for each t year ahead of us, it's going to grow at this amount, but I'm pretty unsure about the details. So this very, easy to type function gives me, it says that for any time I could submit the time and then get what the result would be at that time. And once I have that, it's not too hard to say, oh, I'm going to also figure out what the US population is at every point in time. And then once I have those 2, it's pretty easy to then state like the GDP per person, assuming that these variables are not correlated with each other, which of course is not exactly true, but this is like a first step, is going to be this distribution over periods of time. So in general, this could be a very nice way of doing functions and reusing like very simple models, or hopefully more complex models in the future, while all still like keeping track of uncertainty. So now I'm going to show like one final example. So just say we want to aggregate these. So probability aggregation is a big thing for other forecasting apps. And it is quite easy to do with functions as well. So just say this is my estimate. So if I model that, it's going to look like this, right? This is what I think, this is my forecast for a specific parameter over time. And then this is a forecast of my friend Nora, right? It's like a bit different than that. Then our combined estimate would just be saying that like for every point in time, we're just going to take the a multimodal, which is just a mixture of my estimate at that point in time plus Nora's estimate. And we could graph that, that's combined, and then that gives us this. And you could see that basically the distributions are being split over this period. So in the beginning, things are quite similar to each other, but then the two of them diverge a whole lot. So if I do combine at 1, there's probably a fair amount of similarity, but then as I increase t, then our predictions diverge, and that's basically this split that you see. It would be nice, of course, in the future for us to have diagrams that make that more obvious and just show where the mass is, but this is like a good first step, I think. Yeah, so that's like a very quick tour of the basics of how Squiggle works. There's obviously like a whole lot of work done to go forward, but the main goal is to just start allowing people to write forecasts that are functions that deliver forecasts, which allow people to hopefully forecast just many more things. And it seems like we could still get a lot of the properties that we can out of, basic like distribution forecasts or percentage forecasts. But we also get like a lot of other nice properties, and that you just get a lot more flexibility that comes from functions. So thanks for watching. I'm very curious if people have questions or concerns or like suggestions on how to go forward with this. There's a whole lot that it could potentially do, especially if we were to build it out in different ways. Thanks for watching.